Start recording and share my screen. Okay, so welcome to the week 5 live session of molecular spectroscopy, a physical chemist perspective. So today we will mostly, so till then, while I get the writing pad, I will discuss a little bit about the palm probe spectroscopy, transient absorption spectroscopy, right? What has been discussed. The portion I do not need the writing, so for that part I will show right now. So you remember that at the last uh, part of the week 6, actually Professor Datta taught you the palm probe spectroscopy, right? That not to the details, but he gave a idea of this technique used by Professor Ahmed Jewel for some groundbreaking experiment, right? For which Professor Jewel got a Nobel Prize. The specific experiments were the snapshot of a bond breaking, which of ICN molecule, if you remember, uh, and then the oscillation in the absorption of sodium iodide in ground state, and the sodium neutral sodium absorption. The oscillation was there, right? So these observation were possible because of the invention of the laser, of course. Uh, what are lasers? Lasers are light. Uh, do you know what is the full form of laser, Soumitra? Oh, I think you were not here. So what I was asking that if you know the full form of laser.
Hello, sir. I am available now.
Okay,
Can you
okay.
hear me?
So yes, I can hear you. So do you know what is the full form of laser?
The light emission by stimulated emission of radiation. Light amplification. Light
Light ampli
amplification
Yes,
by
by stimulate
stimulated emission of
emissions.
radiation.
Yes. So earlier, so I will also discuss that yeah, two-state model or a three-state model or four-state model to get the laser. But before that, what I am trying to show you is that the palm pro spectroscopy. I have the nice presentation of it. I will not require the writing pad for this. That's why I am showing you this at first. So the context was I think you missed that part. You were not, by chance, the connection was not there maybe.
Yes. Yes.
So what the context was that after the invention of laser, specifically with the femtosecond lasers, uh, Professor Ahmed Jewel actually shown some groundbreaking experiments, right? Like bond breaking, snapshot of bond breaking in ICN, even the coherent oscillations in the absorption spectrum of sodium iodide when in the ionic form, the absorption shown are decay and a rise time associated in the kinetics of the neutral sodium ion, right? Not ion, neutral sodium atom. So this was possible using spectroscopic technique known as palm probe spectroscopy, also known as transient absorption spectroscopy. So I would like to show you a basics of this transient absorption spectroscopy in this slide. So for absorption, right? For now, we have already told you that your absorption is logarithmic of your incident intensity of the incident light
By
divided by
transmitted light.
transmitted light. So here what we are actually going to monitor, here we are going to use a pump laser and a probe laser. So what is the job of a pump laser? Pump laser is really highly intense light. Okay, highly intense excitation light. It will excite my sample from ground to excited state, and then we will have a probe light. Mostly we use white light as a probe light. As you understand, probe light means that if it is a white light, then it is constituent of all the wavelengths, blue to green to red at certain proportions to get the white light. Now, what we will do is that the pump light is very highly, the intensity is very high. But when for the probe light, the intensity is not that high. Why is so? Because we don't want our excited state dynamics to be regulated by the probe light. So we don't want that population much change in the population. Obviously, we want some change, but not much change with respect to the pump light. So that's why the probe light intensity would be less. But I'll not go into the deeper of that discussion because you have only shown a transient absorption spectra, or the, I would say not exactly the spectra but the kinetic decay of CN star, right? In the lectures where you have seen a rise time. So
Okay.
I will also talk about the rise time also if you don't know what is a rise time. But before that, so in transient absorption, so you have heard of transient absorption spectroscopy before, or this is the first time you are hearing, or in the class you have heard the
Yes,
first time?
in the class I learned it first time.
Okay, so so obviously for fluorescence techniques, you can get the fluorescence lifetime using a technique called TCSPC, time correlated single photon counting. So you generally your that fluorescence takes place. Actually, the emission fluorescence decay takes place in uh, nanosecond scales, right?
Yeah.
But suppose you don't have a fluorescence associated to your sample, then how can we look at the excited state dynamics?
Okay.
What I mean by say that what I mean to mean by that is that if suppose your non-radiative pathway is very high, so
Mm.
your the fluorescence is not there. So so how can we look at the excited state? So for that, this transient absorption spectroscopy plays a crucial role. So here what we look at the difference in the absorption, difference in absorption in presence of pump and in the absence of pump. So as you can see, the equation becomes, and the I0 will cut, right? It will
Mm.
become I no pump by I pump. So what actually happens? Let me show you here. So your actually the transient adjustment spectrum looks something like this. So this is your ground state. This is your fast excited state. And suppose this is your second excited state. So
Okay.
what is, so there are, so actually the spectra doesn't really look like this. This is a very simplified version of the spectra. And spectra is very complicated. As you can see that there could be multiple uh, features associated with that spectra. One is ground state bleaching, another could be excited state absorption, another could be stimulated emission. So if you remember that for the particular example of the bond breaking example, actually the stimulated emission was being probed
Mm.
for that particular experiment. Okay,
Mm.
stimulated emission of CN star. So
Same
what is
story.
the, yes? So if you look at this pointer of mine, what you can see that, so this is S0 to S1 is just a absorption process, right?
Yes.
Then which is light induced. Then
Mhm.
S1 to S0 is also stimulated emission, light induced. What will happen if some of my molecules in the excited state will get uh, so so my population of the S1 state has been done by pump light. Okay. Now I
Mm.
have another source, probe light. Why it is called probe light? Because we are only going to look at the probe light change in the probe light absorption. So probe light means what we are probing, what we are looking at, what we are observing, the change in the intensity, transmitted light of the probe. So the transmitted light of the probe or in intensity of the probe light in absence of pump and in presence of pump. Okay. Now after the pump excitation, some molecule has come to S1. Now they can be excited with that probe light. Here, probe light will acting as a stimulated thing. See, pump light excited our molecule. Now, when the pump light is uh, can stimulate some stimulated emission. It can even stimulate some absorption process from S1 to S2. That is known as excited state absorbance. And
Okay.
with time, so we you can give a delay between pump and probe, only one at a time. So generally, you are excited by your pump and you give a probe using that variable delay what Sarah has shown in the class. And accordingly to that delay, your this excited state absorbance will decrease. Why? Because your population at S1 is going to decrease. So
Yes.
that way, that decay is actually going to reflect your lifetime of the S1 state itself. Okay.
Okay.
So by looking at different features, you can say different excited state dynamics. So why ground state? What is ground state breach? What is excited state absorbance? And what is stimulated emission? That I told you from here. But why ground state breach is going to be negative? Why stimulated emission is going to be negative? And excited state absorbance is going to positive? That I am going to tell you right now. You see at this uh, uh, um, diagram. So see what we are going to monitor the intensity of the transmitted intensity of the probe light in absence of pump, in presence of pump. See the excited state absorption process we are going to monitor. So this is your S0, this is your S1, and this is suppose your S2. Some incident light is there I0, this is I0. Okay. Suppose there is no pump. So your molecules from ground state to excited state, there is no transition, right?
Yes.
So so your excited state absorbance, so there no molecule is going to absorb that this energy level. So so suppose means what I tried to show you in a qualitative manner. Suppose five photons are here, then all of that is not what I should say. It's not so five photons are there, and you are also getting five photons when there is no pump, without pump. So there is no change. But suppose there is pump. So if there is pump, so already some molecule have been excited to the from ground state to S1 state,
Mm-hmm.
and now they can absorb this light. So your transmitted light intensity is going to be less at this particular wavelength when you monitor the energy gap between S1 to S2, because they are already getting excited, so they are absorbing those particular light.
Mm-hmm.
So your transmitted intensity is less. So what you expect in delta OD? So in presence of no pump, there is no change. So I transmitted
Yes.
intensity is more. But in
Yes.
presence of pump, your transmitted intensity of the probe is less.
Yes.
So you are going to see a positive signal. So that's why your excited state absorbance is a positive signal.
Okay.
Now look at the
Otherwise, it will be zero.
otherwise means
Means if there is no pump, in that case, the intensity will be similar. Means I no pump will be equal to I pump. Means I want to say if there is no this no pump in the
means
case
you
of no
won't.
pump.
Yes. So actually the program is so the detector is so what is actually happening. Uh, let me let me go to maybe one of the pump probe spectroscopy. If I get the image, then it will be good to show you. Maybe this one for now. Oh, this is very small. So your pump and probe light it come as a it will fall onto your sample co-linearly. It can fall in a certain angle also. Generally, i- in our
Perpendicular.
yes, no, actually not perpendicular. Actually, in our setup, what we have in our lab, that is actually a collinear kind of. The angle is very less. In
Yes.
particular, you can say the it's a collinear kind of a setup, and your pump light is only used for exciting your samples. Okay,
Okay.
and it is not getting detected. It's actually dumped. Then whatever rest of the pump light is there, that got dumped. But
Mhm.
the probe light is now come at a certain delay with respect to your pump, and it is a white light. As I told you, it is a white light, so it has a frequent quite a broad frequency domain. So that how the probe light can interact at different delay times after our excitation, and it has different kind of spectra, and that is going to be recorded or detector or a detector. Okay, so that's what I was trying to say. If in the detector you are going to detect only this log I no pump by I pump. So if, as you said, that when there is no pump, actually what I mean to say that at for this particular uh, energy gap S1 to S2, or this energy gap doesn't really absorb. So at this particular point there is no change. Okay, but this pump is not only for this wavelength only. It so as it is a probe light, I told you this probe light is a white light, consists from maybe 300 to 800 nanometer. Okay, now I am particularly talking about this energy gap. Let me use for this energy gap. When there is no pump, you are going to get almost same intensity. So there is no change. But suppose
Okay.
now there is ground state breach. Then what is happening? Then in ground state breach means there is no pump, but your probe wavelength is such that some of your uh, molecule can ground state molecule can absorb that probe light and go to the fast excited state. Okay,
Yes.
so what will happen? Your transmitted light will go down.
Mhm. Yes.
Now in presence of pump, so see your ground state population is already less because there is pump. So when there
Mhm.
is pump, so the ground state population is less. So your light absorbed in light of the probe light absorbed by the ground state molecules in the ground state are less. So your transmitted light is comparatively high. Right? You got my point,
Okay.
what I'm trying to
Yes.
say.
Yes. Yes.
So
Yes.
now if you look at the delta OD value, your I no pump transmitted light of the probe in presence
Mhm.
of pump is more than the no pump. So
Mhm.
you are going to get some fractional value here,
Mhm.
and that's why logarithmic of the fractional is going to come as negative. So that's why for a ground state bleach process, you observe a negative signal. And suppose there is another process, stimulated emission. So in stimulated emission again, you get the idea, right? What is happening in the without pump, so all the molecules in the ground state. So
Yes.
the probe light is not facing any molecule in the excited state. So again,
Okay.
there is no change in the intensity. Transmitted light is same as the I zero for the pump probe
Mhm.
light. So for the probe light, but in the class also said mentioned about this net gain plus net loss, right? So here you
Yes.
see in presence of pump there are some molecule in the excited state, so they are going to get stimulated. Okay, and they are going to show some stimulated emission. So these photons are already there, plus they are going to add some more intensity. There is some net gain due to
Yes.
stimulated emission. So obviously, like that, your eye transmitted in presence of pump is going to be more than the no pump. So actually in no
Mhm.
pump there is no change. But in case
Yes.
of pump, it has increased in the stimulated emission area. Huh.
Yes.
Why I'm calling it a area means there are different frequencies, right? So these energy gap, those are different.
Yes.
So your stimulated emission also you are going to see a negative feature. But what I'm trying, so this is the basic idea what I'm trying to tell you right now. Let me look at it. Uh, okay, so this is what I wanted to convey you about the palm spectroscopy. As it was discussed a little uh, in the course, so I thought it might be a good idea to give you the basics that why the ground state bleach is negative or excited state absorbance is positive. What is the actual feature that has been monitored in that ICN experiment by Ahmed Jewel? So, for now, you remember that there are two potential energy curve for ICN, right? One, so from there, Sarah has said that the pump was used at 308 nanometer. So from ground state, the molecule is excited to the ICN excited state, and it belongs to a dissociative potential surface. So quickly it comes to I plus and Cn minus, and that Cn minus can absorb that uh, particular 388 nanometer, or it can emit at 388 nanometer. Okay, the stimulated emission 388 nanometer. So so that has been monitored, or that has been probed, that part of the light has been probed after excitation. That is why it is called a palm probe spectroscopy. So it's a very state of the art technique. Right now, so it can be visible pump, visible. So the setup we have at our lab is a visible pump, visible um, uh, probe wavelength. So you can excite by the visible region of the spectrum, and you can look at the visible part of the probe. But there are more sophisticated instruments out there. Now we are also planning to get some of the instrument in the upcoming time to look at the visible pump and maybe the NIR probe or IR probe. So there one can look at the vibrational changes in the excited state. So right now what I'm trying to show you here, the spectrum, this is a particular delay. Okay. Now the delay between the pump and probe is variable. There are going to be much more points, right? So this is just a snapshot at a particular delay. Now, with changing the delay, the spectra generally changes. Okay, let me maybe give you a um, data how the palm probe data generally looks like. Maybe we can go to online from our lab. Let me show you the data we collected in a palm probe spectroscopy. Maybe we have it here. So in the discussion session, we can always go ahead and look at some processes. But see, this is a palm probe data. Okay, see, uh, let me zoom out maybe. Can you see this?
Yes, yes, sir. We
Yeah.
have seen.
So as I told you that actually the palm probe, so this is actually a spectra taken at a 400 picosecond time scale. Okay. Then this is at 1 picosecond. They are different, but see there are 1 picosecond, 400 picosecond, and for maybe 40 picosecond and 400 picosecond, like that. So this is how. So from here, what you can see there, this is a bleach feature is there. Then there is some positive feature. You already know the positive feature is excited state absorbance is there, right? So that's how. So this is a spectrum, and with varying time. So at 1 picosecond time, at 400 picosecond time, your spectrum looks different. Okay. And when you look at a particular wavelength, okay, suppose you are going to monitor at 350 nanometer. Okay. So
Okay.
this band. And now you are changing the time or the delay. So then you look at the kinetics. So this is your spectrum and or spectra, and this is your kinetics. See at the kinetics is different, or it may looks like this. I hope you are getting an idea what a transient absorption data actually looks like. Uh, and look at the spectra, look at the y-axis, delta absorption. We
Yes.
look, yes, thank you, sir.
So in the exam, what kind of question do I expect? Means this
So
kind of.
no, by these actually I wanted to give you a brief example of how a transient absorption data looks like and how what is it. So the experiment that has been carried out. See, so Sarah has shown you the snapshot of bond breaking of ICN. What I am
Yes.
telling you for a long
Yes.
time. So this is
Yes.
the kind of this kind of a kinetic data you have already seen here.
Yes.
The column, the panel C. So, so that's what I was trying to say, that how that kinetic data has been obtained and how that data can be analyzed, or idea behind it. So maybe the in question you are not going to be asked directly from the pump probe spectroscopy or the basics of pump probe spectroscopy, but this is what I intended to discuss so that you get a idea that what transient absorption spectroscopy is, what is has been discussed in the class. Okay, maybe some numerical question may come, not numerical, but I would say some, I don't know if I if I say philosophical kind of question, that that particular experiment, from that particular experiment the question may come, that what is the feature in the that experiment has been looked at for the Ahmed Jewell's bond breaking experiment. So so you will mostly the kind of question asked in the assignment, na? So those
Yes.
are the kind of question generally comes in the exam also. Not
This
very
type of
difficult.
question I will expect. I'm going to expect in the exam. You want to
The
say?
the kind of question has been asked in the assignment
Okay.
mostly, mostly. But I hope you got a taste of the transient absorption data.
Yes.
So maybe I can show you some more if he has it. So these are the data from my lab actually. Maybe you can show you some more. There are many processes, FCAs, many spectroscopic processes that can be used, but that is not intended for this particular course. I just wanted to maybe, I'm not sure if the data is here, but by looking just at the data, you may get some feel that how the absorption. See, this is another um, transient absorption spectra. Different kind of kinetics has been studied from here. But let us get back to the main topic. I got actually my professor just gave me the writing pad, so let us come back to the teaching part. So, so I told you this, and uh, coming from the you had a question regarding that stylized A, right? Or no,
Yes.
not the stylized A. Also, and another question you have from the yeah, the stylized A
PMA.
question I have not cleared yet. you have the question that regarding the selection rule, if someone is using algebraic method or the
Mhm.
numerical method to get the wave function of a vibrational level. So
Yes.
anyway, see, that has been shown, right, that the algebraic method and these numerical methods both actually yield the same equations, right?
Yes.
So eventually, your that particular question, I told you, no, that if numerical method has been discussed, then so it was a multiple correct answers were there, right? So I
Mhm.
think one related to the recursion formulae of the Hermite polynomial, and another something was there. What I am not remembering right now. But what I'm trying to say that at the end of the day, whatever method you follow, you are going to yield the same wave function for a particular state, right?
Yes.
For a particular v equals to 1, v equals to 2, or v equals to 3, you are going to land at the same wave function
Mm.
if you use the algebraic method or the numerical method, right? So
Okay.
so ultimately, your selection rule is going to be the same. It
Yes.
depends that which method you are following. And in the class, the algebraic method, the Hermite polynomial was being used, and that's why the question was like that. If so, you want to look at the transition moment integral if your directly the wave functions are given, then it may be different. You got my point, what I'm trying to say? Then you can directly calculate the transient moment integral using those wave function. And eventually you will see that they are going to be orthogonal or something like that. And if v delta v equals to not equals to 0, not equals to plus minus 1, something like that, you are going to see that that transition moment is not going to, the integrand will be something like symmetric or anti-symmetric maybe, so that the total PMI is going to be 0. Okay, so
Okay.
it depends on the method. Ultimately, you are going to land at the same wave function. That's what I wanted to say. Okay, now for today's discussion, let me start with the Rabi oscillation maybe. So
Mm.
in the concluding remarks one, Professor Datta has mainly discussed. The first part was like uh, the the modulus of the Cm square. What is Cm? Can you tell me what is Cm?
Cn is the coefficient of that state. Actually, Cm square
Excited
basically
state
tells you, yes,
or the
basically tells you,
or
basically
the
tells you the probability of getting that state.
right. And we should not say the excited state. Maybe it is better to call it the final state, right?
Yes.
Because
Yes.
it can be associated with absorption, it can be associated with emission, right? So better to call it the final state.
I have a question that they asked in the week 4 assignment.
Yes,
That answer is out now. So they asked about the probability of transition between two states is
yes.
independent of this. There are four options are there. If
So
I can recall.
we will discuss that, or should we
Okay, okay,
discuss
okay.
that at first and then maybe we can
No,
come to
no,
this?
no, no, sir. We will discuss it later. So
Okay,
first,
okay, okay. So this is so I told you no earlier that I also had a doubt that how that mu lm
yes,
earlier it was along x direction, and it has been taken mu lm by 3,
yes,
and it has been come. So I think in the class also someone asked that same question maybe, and I saw when I look at the I was also reading means looking at the lectures videos. So there
okay,
I saw that someone asked the same question. That's why I have also written it as a constant. Sarah also changed the. So it was not required. The three was not important. The
yes.
mainly this electric field along x-axis, or the transition moment integral, and the this sine function or the time dependent thing was required.
Okay.
So from here, actually, for Rabi oscillation, actually you look at the oscillation of this square of this contribution, or you can say contribution, square or the probability, right? So
Yes.
that is going, if you plot it against time, what you are going to see is that it is going to follow sinusoidal wave function. So this sinusoidal wave function is not going to be negative, obviously, because it's square of something, right?
Yes.
And it would, so at t equals to zero, you can see what you are going to get zero, right?
Zero. Yes.
At t equals to zero, and
Yes.
it is going to be some kind of oscillation. So at some time it is going to be maximum, and then
Mm.
it will fall, and then it will again something like this. Sorry for the bad drawing. Something like this.
Yes.
I'll not draw much. It's getting worse and worse. But what is this point? So at after zero, at which point it is again going to be zero? So that
At
is
five.
here.
Yes.
So you means your sine function is going to be zero, and your
Yes.
sine is
Yes. Yes.
zero at
Sin
n
pi
pi
is equal to zero.
n pi is equal to zero.
Yes. Yes.
So
Yes.
you will see that the first is zero at t equals
Mm.
to zero. Then it is going to be uh,
H
and
by pi.
so actually you can also write it in other way also. So this part could have been written h mu zero, which is
Yes.
your the difference between these. And so maybe I will write it like that and would be a little cleaner maybe. So maybe I will remove this h also. Mu zero minus nu, right? And
Yes.
here mu zero. Okay. So you will ultimately see that at t equals to t is going to be here. At the first, it will be going to be nu zero by nu,
Yes.
and here it will be a multiple of n multiple of where your oscillation is going to reach zero, and it is going to have some maxima, right? Right, and
Yes.
this maximum value is, and you can also change this to your energy density, which is equals to your E0x square by 2 pi, right? So again, so let me, maybe I can write it down here once. Some constant is going to be there. It is going to be rho nu. So ultimately, your some constant, okay,
Yes.
multiply by your energy density, multiply by your modulus of the transition moment integral,
Yes.
and your
Divide by u
mu zero by mu.
whole
From
square.
here, what are the and also
Yes.
yes. So from here, so here you are plotting your CM square. So from here, what are the things we can look at? That when what is the maximum value we can get it? It depends on our so we obviously want during a transition what we want. We want this CM value to be maximum, and when it can be maximum, the first option is we
Nu
excite
tending
with
to nu
very
zero.
highly. The energy density of the light should be very high.
Very high.
So that is one condition. Then obviously transition moment integral is favorable, is
Yes.
maximum. And another condition is your Bohr resonance condition, or you can say the resonance condition. I should not say Bohr resonance condition, I should say resonance condition. Bohr resonance condition is that Em minus El is H nu. H nu, H not nu. This is your Bohr resonance condition. But this, what I tried to say is this energy gap, this nu zero minus nu, if it is very going to be very close, then only your overall value is going to shoot up. Or if this is very far, nu zero and nu is not equal, then it is going to be a large denominator. Overall value is going to decrease. So
Yes.
it should be less. Okay, and how can we get that? It will be less when you are providing it a particular, so the energy gap, so your energy of your excitation source should be very close to the energy gap, and then only you are going to see the transition. Okay, but here what are the other things you need to look at? That when your nu zero minus nu is, so your nu zero for a good transition, or a better mixing of states, your nu zero minus nu should be very small. So your overall 1 by nu 0 minus nu time. So this is going to be very high, right? And this is actually going, is actually time, right? It actually denotes time. 1 minus nu 0 by nu, right?
Yes. Yes.
But we are in ambit of, we are actually obtained this equation from a time dependent Schrodinger equation and application of perturbation, right? So here our light or the laser, I should say light or the radiation. So perturbation is our radiation, electric field of the radiation, right? So that, so as we are calling it a perturbation, so it should be small, right? And the small perturbation time dependent, so it should be operated for a very small time, right? But as you can see, for a better mixing of state, this 1 by nu 0 by nu is very high, this term. So actually, what we actually look at during a transition is this part of the oscillation. So we don't really look at the total oscillation. We only look at, or what we look at this position. I hope if you had some queries during the class that is now, you might have some clarification on that. Okay.
Sir,
So
can you please?
yes,
This is basically to equate this nu and nu zero will be very close to.
yes. So
Actually,
for a better
not
mixing of
very close.
states,
Yeah.
so there are two conditions, right? Hey, three conditions here to for a better mixing of state. So this m square will be high, means the transition is better, or the mixing of states is better, right? The transition is better late. So when that can be good, when this is highest or this is maximum,
Mhm.
when it is maximum, when your gap between nu zero and nu is less.
This rho nu must be higher and nu zero is tending to nu.
So along with this condition, this is another condition,
Mhm.
the third one, that the
Yes.
gap should be very less, right?
Yes.
So if the gap is less or the frequency difference is less, then your, actually your frequency is going to be very large, right? Or I should say frequency is going to be very small. I'm sorry, frequency is going to be very small, right? So see, it will come at a very, so your frequency is small, your tau is large, or t is large, frequency is small. Okay. So as you can see, if it is high, sorry, if the overall 1 by nu 0 by nu is high, then actually we are not actually looking at the oscillation, the total oscillation. We are looking at the fast part of the oscillation, because we are in ambit of the perturbation theory.
Okay.
We should not excite the sample with uh, what I should say that the time dependent Schrodinger equation and the perturbation theory application of the perturbation theory is dependent, and this equation, whatever equation we are writing like now, this is applicable when it is the light is applicable for a shorter period of time, not a long period of time. As sir mentioned that if it is in presence of uh, much more time than in presence of light, then some other complicated term would have been added to this equation. Okay. So, so in our discussion, what we understood that for a better transition, your energy density of the laser should be or the light should be very high.
Yes.
So, what is the source? If our source is a laser source, then that energy density is going to be very high,
Mhm.
right? It can
Yes.
be tunable, right?
Yes.
So
Yes.
these two factor can be worked out, or I would say that these two factors are being taken care of if you use a laser. So when you use a laser, then your obviously if your transition moment integral is zero, then if you still use a laser, then you are not going to get some
Okay.
spectra, right? But
I have a question. This
yes,
CM square is basically tells you the probability of transition.
probability of transition.
Transition. Okay. So in that equation, it only depends on the rho nu mu
Yes,
lm square and nu minus nu zero minus nu whole square. Okay. So
yes,
what I understand, your intensity will is desired to be higher. We
yes,
means if intensity is high, your transition probability will be higher. And mu
yes.
lm basically it is a quantum phenomena,
Hmm. It's a
and
space
mu
dependent phenomena, right? Space dependent phenomena.
space dependent phenomena. And this nu zero minus nu is basically we want monochromatic light.
Right,
That is close to the energy gap between these two states.
right. New zero.
Yes, that's all you want to say, na? This
Yes. So
CM
your
square is,
frequency of your laser should be very, very close to or equals to your energy gap.
and there is no mention of time. Means we don't have to bother about the time of perturbation.
Uh, we have to be means in other way the time is very the interaction or the perturbation is acting for a very short period of time.
And that is the basic assumption that we have. Means
Right.
we are using this
Yes.
time dependent. That is your assumption that we are this pumping this all these things for a very short time.
Right.
Okay, in this equation, I don't find any direct relationship between T and your CM square. Am I right?
No, so for that your actually the time dependence actually coming from the sine square part. If you look at
Yeah.
this, so
Yeah.
there your pi t is there, right?
Yes.
So so you this is your amplitude. So
Yes.
this is your amplitude by, but your amplitude actually varies with time.
Yeah.
But we are looking at a very small period of time. That's what I am trying to say. If it was a means if and then also the equation would have been much more complicated. Some other terms would have been there, but still some damping oscillation would have been there. It would not be the same. So the maxima here for the first peak and the second peak it was not going to be the same. I think Sir also mentioned something like the damping oscillation. Did Professor Datta mention in the class? I guess so. That when those when you mean the perturbation time is long, then you may experience or expect some damping oscillation associated with this amplitude of this EM square. So with time, the amplitude is going to be decreased. So this is for ideal situation what we are discussing, and we are looking at this very small time period. Not also it is not like that it is going to the maxima also, right? Not all the molecule can for a by one excitation you cannot So suppose there are 10,000 molecules in the ground state. By that excitation, you can only you can excite 10 molecules, 100 of molecules, not 10,000 molecules. Okay. Okay. Now maybe we can. So I will not go to the very deep onto this, but as sir mentioned that what is the main thing is going to main theme is going to be the population inversion, right? So the thing just I told right now, how can we get a laser? So till now we are discussing that if we excite it with the sample with a laser, then your transition probability of transition is going to be high, right? Now, how can we make a laser or how laser is being created? So obviously it is stimulated emission, right? You yourself only told me that it is light amplified by amplification of light by stimulated emission, right? So stimulated emission is associated. So for a stimulated emission, you and for a laser, what we have discussed that you are going to need population inversion. Means your final state and your excited total. So your population of the final state should be more than half, right, of the total population. So the method, I'm not going into the mathematical derivation of that rates and all, but maybe I'll just write if uh, the last or the final term. So for a two-level system, I should say for a two-level system, we have discussed two-level system in details, right? Right in Einstein model or in the Fermi Golden rule discussing that. So the it's going to look like so B is your Einstein coefficient, right? And then it is 1 minus e to the power minus 2b rho nu plus 1 multiplied by t. Okay. So from here, what uh, the final equation, what you can see for a two level system, if this is my, um, if you are going to plot, so with time, okay. So what you can see, so with time means, see, in the quantum mechanics, uh, by time, when we mean by infinity, na, so it's or even the distance, infinity. So that infinity is like the macroscopic world, what is finite. So in quantum mechanical dimension, what is infinity? So in our macroscopic world, it is all actually finite. So in 1 meter, in quantum mechanical domain is actually infinity. 1 minute or 1 second. So this is actually infinity in correspondence to a femtosecond process, right? So so when actually in question or in theoretical knowledge, when they say infinity, if you actually take the course by the Professor Datta has an NPTEL course on the quantum chemistry also. If you take that, you will get some further idea about that. I'm not going into the details, but as you can see, when the t is zero, so your exponential term is going to be zero, right? One. So no, e to the power zero. Yes. So one minus one. So overall, it is going to be zero, right? And now with time, suppose t is infinity. So here I don't I by infinity I am not trying to say it is 1 trillion years. So maybe 1 second, something like that. Okay. So when your t is that, so you will see that. So if I take t as infinity here, then your exponential this part is going to be zero, right?
Yes.
Then
Yes.
it is only going to be left with 1. And then what are you going to see that your nm by n, actually I might have miswritten this. So your n should not be there. So now you will see your, it can reach a saturation value at infinity t, and that value is b rho nu by 2b. It's not really a saturation value. This is actually the value it follows at infinity, right? And
Yes.
that value is actually going to be less than half. Why? See,
Because two system, yes, A is there. A is always positive if B is there.
right. So if there is some absorption coefficient is there, some absorption is there, then there would be some spontaneous emission. So your A is never zero, and that's why it is going to be always going to be less than half. So if I take this line to be half, so it is always going to be like this. Okay. And that's why from a two level system, you can't expect a laser. But what about a three level system or a four level system? So from a three level system, you have already seen that two kind of examples, right? One was pulse laser and another was
Continuous.
continuous one. So this kind of question can come during the exam that for a three level system. So obviously it will be a MCQ or MSQ kind of a question, but the that concept can be useful. Okay, for a three level system and four level system. I'm not going into the deep of that, but ultimately what we learn that the population inversion can take place in the three level system or four level system. Can you give me an example of a four level system where the laser uh,
NDF.
NDER?
And
So NDER. Okay, that's actually a good answer. Why? Because I want to mention that if you remember the laser part, so there is something called active uh, medium was there in the laser cavity, which is which will get excited by your once or sometimes by your your excitation source, and then the stimulated emission will take place inside the laser cavity. One side will be the high reflector, and other side is going to be your output coupler, right? Your high reflector is going to be 100% reflective, and your output coupler will be something like 99% or 97%, something like that. The reflectance is there, right? So
yes,
as you mentioned, Nd:YAG, neodymium, yttrium, aluminium, garnet. So in that, your neodymium is actually the responsible ion for that particular emission. Okay, and its fundamental emission is around 1064 nanometer, and the second harmonic of that is actually 532 nanometer. The green laser, 1064 nanometer light you can't see by your eyes, right? It is in NIR region, near infrared. So actually the most of the time Nd:YAG laser is known by the green emission 532 nanometer, but you have to remember that the fundamental emission of the primary emission is not in the visible region. It is 1064 nanometer, and that is being used by a nonlinear crystal. It has converted to the second harmonic of that is actually 532 nanometer, which we observe, and that is actually a continuous wave, right? If you remember the why it is a continuous wave, because the if I draw the four level system once, so this is your one, two, three, and four, and so your excitation can form one to two, and then this
it
is
will
this is
non-radiative behavior.
non-radiative, right? So non-radiative radiations are actually denoted by these kind of arrows. sorry, these kind of wavy arrows, and the straight arrow generally being given to the radiative process. And also your level 4 is also uh, is going to be depopulated very fast using the non-radiative process. So
Yes.
even you have multiple molecules here, your population inversion can be done from level 3 to 4.
Yes.
Okay. And you see this energy gap could be very less. And I just discussed your ND gap, which primary is 1064 nanometer, right? So if it is 1064 nanometer, see the energy is very, very small, NIR, right?
Mm.
So that's why the energy gap between 3 and 4 is very, very small also. Okay. And even if you have one molecule in the third, and as I told you that this level, actually the fourth energy state is going to depopulate very, very fast. So this emission is going to be actually continuous. Okay. You are going to get continuous kind of emission from here. Okay. Now, next that has been discussed in the class was the use of a laser. So, can you, before use of a laser, and obviously after that, palm probe spectroscopy has been discussed, but due to that unavailability of the writing pad, I discussed that earlier. Anyway, can you tell me some properties of a laser, basic um,
Means highly
fundamental property?
monochromatic, highly
Mono,
monochromatic and
right?
intensity. Yes, intensity. It will be monochromatic, then high intensity, then phase. It's highly means in same phase.
Same
Means
phase. Coherence. Coherent, do you mean by say coherent? And
yes.
any
Other
other?
the
I am also forgetting. There are four. So highly intense, then coherent, means the phase are same, and then your monochromatic,
mm,
and what else was there? I also forgot. Anyway, uh, but uh, what are the use of these lasers are going to be? So obviously the first was discussed in a context of the spectrophotometer, resolution of the spectrophotometers, right?
yes.
Then it was discussed in the controlling the reaction paths depending on the attractive and the repulsive pathway, that how much energy you are going to provide to the your your sample so that the oscillation will look like what, right? And then the birth of femtochemistry by Professor Ahmed Jewel using the femtosecond uh, pump spectroscopy, right? Or the using of femtosecond lasers. But here one catch is there. We are always saying that lasers are highly monochromatic.
Mhm.
But when we are going to discuss these ultra fast lasers, so ultrapulse means the lasers with the FWHM in femtosecond scale. Okay.
Yeah.
So the full width half maxima. So this is a very common term in the optics, full width half maxima. So
Yes.
suppose this is your laser pulse. Okay. So full width. So this is full width at half
Mhm.
maxima. Okay. So
Mm.
it's not like that it is going to be outside the pulse. This is your FWHM. So if your FWHM of a laser pulse is in time domain, if it is in femtoseconds, then the accordingly to the Heisenberg's uncertainty principle. So if there is the uncertainty in the, so what I'm trying to say, ultra fast laser. So your pulse width is very, very small. So if your pulse width is very, very small, then uncertainties with the pulse width is very, very small. So you're in the time domain. So if in the time domain your uncertainty is small, then obviously in energy domain it is going to be very very high, right?
Yes.
In
Yes.
energy domain means in frequency domain. So if then what is going to happen? It's not monochromatic anymore. So it doesn't mean laser doesn't always going to mean it is going to be highly monochromatic. It can be it can be polychromatic depending on the your type of the laser also. Okay.
So can you give an example of this kind of laser? What kind of laser is used for this ultra fast?
Okay. So maybe I can give you an example of titanium sapphire lasers. Even the titanium sapphire laser is a very common oscillator, or you can say active media, where titanium is again the active media, and the sapphire is actually the substrate. And in case of ND YAG, we discussed, right? YAG is the substrate, right? YAG. YAG is
Yes.
substrate in the neodymium YAG. Yes. So titanium sapphire, these can produce very pulsed laser with ultra fast FWHM in hundred of femtoseconds. Okay, so like the transient absorption instrument we have in our lab is actually a femtosecond transient absorption spectrophotometer. Okay, maybe in one of the maybe in the next lecture I can give you a tour of the by video conferencing. In the live lecture I would like to show you the palm probe instrument we have, maybe on the next lecture. That would be actually a good exercise. Anyway, so your titanium, so the output of that or the emission of that titanium laser is actually a very ultra fast laser, pulse laser, which is around 100 of femtoseconds. So you will see in when you look at the spectrum, your spectrum is going to be very very broad. Means actually the output of a titanium sapphire laser, the fundamental is at 800 nanometer,
Okay.
but you will see it can consist from 750 to 850 nanometer in the tail range. So do you get my point that what I mean by the uh, mm, polychromatic, or in ultrafast laser what kind of
It is the
polychromaticity?
result of this uncertainty principle.
Yes, and it is due to that uncertainty principle.
Yes, yes, yes.
So another example I would like to maybe discuss, maybe I will show you again, maybe some other. So the TCSPC instrument we have in our central facility at IIT Bombay, that uses, obviously we can use diode lasers, but we generally use a Mitai laser. Mitai is the company name. The oscillator is titanium sapphire, so it has a fundamental around 800 nanometer. But the FWHM or the laser is actually very ultra fast. So the individual pulses are something like 100 femtoseconds or even 80 femtoseconds. So while recording a decay, we have to be very very careful regarding the scattering. So if whenever we are, suppose we are going to measure a decay, fluorescence decay. So what we actually generally do, we excite the sample and record the decay at some emission wavelength. Okay. So actually in this lecture only you have been taught about the fluorescence lifetime also, right? So the fluorescence lifetime can be recorded using that kind of instrument, TCSPC, time correlated single photon counting. But the TCSPC we have, the excitation source is a MITI source, which uses ultra fast lasers. So we had to be very very careful regarding the scattering component, because as I told you that even if I know I am exciting it with a 450 nanometer excitation wavelength, as it is a ultra fast laser, in the time domain it is very very small FWHF, but it can have a very long tail region to even up to 500 nanometers. Okay, so if I record my decay at 500 nanometer using the monochromator, obviously I select my monochromator to record the to fix the emission wavelength. So there I can see some scattering component, and that is actually coming from the excitation laser itself. If it was a monochromatic source, then that problem would not have been arise. Okay.
Okay.
So these are the some benefits, and obviously using a femtosecond laser, you can look at the femtochemistry, femtosecond domain of the reaction rates, the bond breaking, bond making, this kind of reaction you can follow. But the monochromaticity is the point you have to lose there. Okay, so there is obviously there is some gains here, there is some loss, but obviously the kinetics you are going to look at, you won't that won't be possible without the femtosecond lasers. Anyway, I hope you got the point what I'm trying to say. Now maybe we can move out to how much time we have. We are almost discussing for 1 hour. No problem. We can discuss the first the assignment problems, and then I will come to the some numerical problems. Okay. So the first question, that probability of transition between two states. This is the question I think you were asking at the beginning, right? The
Yes.
probability of transition between two states is independent of time of perturbation. Obviously,
I choose,
it's not.
I choose, yes, I choose that option only.
Acha. But see, as I told you, the time of perturbation is going to be very, very small, right? As you means these questions are given before teaching the Rabi oscillation, right? If that
Yeah.
portion would have been taught, then maybe you would have guessed the right answers. So obviously, it is going to be oh no, time of perturbation is important, but it's for a less. The question states that it is not dependent; it is independent of. So it
Yes.
is independent of energy gap between the states, but it actually depends on the time of perturbation, but very small time. That the this part, this part, it actually depends on time, but very small perturbation. Okay.
It also depends on this new zero part is there. How can you say that it is independent of the energy difference between two states? It also depends on new zero also.
No, your
This kind of question,
energy difference is H E M minus E L,
yes, that is H
which
new
is
zero.
H nu zero.
Yes,
But
yes,
here it is nu zero and nu. Nu is your frequency of your excitation source,
yeah,
frequency of radiation maybe. Okay,
yeah, okay,
and these come from the your energy of the gap, energy gap.
yes,
So
yes,
this is fixed for a particular molecule. This is fixed. So you
okay,
are
that is,
playing with this nu. So frequent. So that matters. These new matters. These new zero actually fixed for a particular molecule.
okay.
So that's why it is independent of the energy gap of that molecule. The energy gap between the state is not, it's independent. But energy density of the light is also
If I give you, let's say, two states, one has higher energy difference, and I give you two options. Let's say you have two states where the
Mhm.
energy gap is lesser, and in the another case, second case, the energy gap is higher. So
Okay.
where do you expect the probability of transition will be higher?
It doesn't it doesn't really matter in this case. Oh, but what I understand what you are trying to say, that when the energy gap is lower, the
Yes, yes,
transition should be more. But it also
yes.
depends on the selection rule, right?
Yeah, yeah.
It
Yeah, actually, this type of questions are make multiple options will be. I think you can choose
yes,
multiple
I
answers will be there.
I got your point, but see, when you are discussing the probability of transition, then again you have to look at the expression that is given, right? Cm square, modulus of Cm square, which is actually Cm star dot Cm, right? Product of Cm star and Cm. So there you will see that time dependent part is there, but very less. Now, energy gap of the state nu zero is constant there,
Yes.
but actually, that has been, I think, also discussed in one of the lectures. I'm not sure which one. During the that Fermi Golden Rule and discussing that part only, sir has, I think, discussed once that H nu zero is, let's take that to be constant, something like that.
Yes. Yes. I mean,
And
this type of question are a bit confusing. Means,
true.
uh, from your point of view, you are right. From my point of view, I may be right. I may
Okay,
be wrong.
let me give you the point you are asking. Huh? You said
Yes.
that there are two energy states. In one case, it is the energy gap is less, and in another
Yes.
case, the energy gap is more.
And from your point of view, what do you
N-
want to say that
n-
in the case two states,
See,
the energy difference is same.
See, it
In,
actually doesn't really depend on the energy gap between the states when you are going to look at the third condition. What was the third condition? Third
energy
condition
density.
was your no obviously energy density, but your frequency of the light you are going to shine on the matter
Yes.
is have to be equal to the gap, energy gap. So
Yes.
it doesn't. So it depends on the radiation you are using. You are exciting your sample. So even if your energy gap is more, even if your energy gap is more, it depends that which radiation you are using. You are exciting your sample with. So if you excite your sample with H nu and it is the gap between two states are H nu zero and your nu zero is bigger than nu, then your transition won't take place. Same
Yes.
here. Suppose this is H nu not dash. Okay, the energy is less. And in that case, your nu zero is going to be equal to suppose your nu not dash, then what you are saying is true. But suppose your nu and nu zero they are going to be equal. Okay,
Okay.
but your nu zero bar is very less than your nu, then you are going to excite to some other state, not to this state. So this transition, even if the energy gap is less, it depends on the energy of the uh, excitation you are providing.
Yes.
So
Well,
actually it is independent of the energy gap between the states.
I think in the last discussion we discussed about this spontaneous emission and this yes, induced spontaneous emission and this induced emission. In that
Right.
case, if the energy gap is less, one can expect this spontaneous kind of thing. So it may it's a kind of this.
I understand your point, what you are trying to say.
Yes, yes, yes.
Uh, okay.
It's point of view. You are right, of course, from your point of view. I may right or I may wrong. Yes,
No, no,
it's actually how you are looking into the matter.
your point is valid when you are thinking of it in the perspective of actually the spontaneous emission. So
Yes,
when the spontaneous emission takes into the matter, then also you need to actually take into the
exhaust probability of transition.
yes. Then also the non-radiative processes also come into the picture. That is another problem, which
Yes,
was
yes, yes,
not discussed in the Einstein treatment.
yes,
And
yes,
I think it is invoked during the discussion of the fluorescence lifetime, I guess.
yes, 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 yes.
Okay. And what else it is in? It is going to be independent of monochromaticity of the light, right?
Monochromaticity of the light. Okay.
So it has to be close to your nu zero has to be close to nu. It can be nu zero means in that region. it may not be monochromatic. Your new could have been a so as I told you just before that, that ultra fast lasers are not really highly monochromatic. There are deviations from the monochromaticity, right?
They
But
only
the transition can takes place in that
Yes,
case.
they only give only one answer. The answer is monochromaticity of the light.
Okay, they have given only one,
One
but
answer, yes.
oh, then I have to check with them. Okay, okay.
Yes,
I have not checked it from their website yet. I just look at uh, the theory part and I was looking at this. Okay. So you have selected the time of perturbation.
yes, yes,
Oh, that's why you are discussing that time that time of perturbation is not going to matter. Okay. I got your point. I got you. But time of perturbation actually matters, but very short period of perturbation.
yes, yes. I thought that was understood. Means while we are considering this time-dependent perturbation theory,
Hmm.
that is understood. Means we have to consider only the short time of perturbation.
Okay. 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 Now let us go to maybe the question number two. Time dependent perturbation used here is of what?
First,
Fast order. That's why your kinetics, what you are going to see is also fast order kinetics, right? The decay or this. Okay. Now fast order. Let me correct it here. Okay. Now natural line with arises from what?
this
Sp-
time-dependent part of the wave function.
time dependent part of the wave function, right? Because again the Heisenberg uncertainty principle.
Yes,
Okay. Then four, space time actually it should have been space, I guess it is written space. But space time dependent wave function of a system is capital psi xyz t.
yes,
So they wanted to know the actually the formula. I think you already know it is C, right?
yes, yes.
This is space dependent and this is going to be the time dependent. But I think they have missed the H divided by H part, right?
Yes, yes.
But obviously, you can see that the first
You
option is
can,
incorrect.
yes, yes. You can
Second
take
option is
yes.
yes. You can see that maybe the E
Take,
value, E itself, actually E is your a constant, and your Planck constant is also a constant. So maybe they have taken it along.
in some
Okay.
cases, in physics, in some problem, they took H cross H1. In some problem, they
But
took.
atomic unit, something like that, not actually one. If your H would have been one, then your
They
uncertainty.
actually normalized it. They actually, in that problem, they actually normalized it.
Okay.
Means in all this problem, they took H bar as one.
Okay, yes, but one you have to use some unit also,
Yes,
one
yes, yes,
atomic unit.
yes.
Okay, now five. Question number five: a spectroscopic transition in the language of quantum mechanics is what?
Mixing of states.
Mixing of states. Good. Now question number six. It's again interesting question that for transition between two states, we obtain this expression, right? The rate of change of the amplitude. This where there is your transition moment integral part is there is a time dependent part is also there, right? Now where your perturbation, the perturbed Hamiltonian, I should not say perturbed Hamiltonian, I should say the perturbed part or the correction, the perturbation correction is dependent on here, the wave function depend on space not time. Is it correct?
Hmm.
Uh,
Actually, wave function.
I think it's the question. Okay, where H dash is the perturbation correction. Now they are given us some statements that the wave function psi depends on space, not time. Is it correct? It's not correct, right? Your psi is a total wave product of your space dependent part and time dependent part. So
Yes,
it's not
that was
correct.
the option I choose, but I choose that the integral is over the space. I choose the integral is over the space, not time. Okay.
But you have to choose the correct options, right?
Yes.
But here the first option
The
is
second
your wave
option.
function. Acha.
Yes.
The integral is over space, not time. That is correct. The integral is here this transition moment integral, right? It is correct answer. In the answer, is it the wrong answer or is it correct?
No, it is the one correct.
One of the
It is
correct.
not the only one.
Okay.
It is
So
not the only one.
let us read the other one. The wave function depends on space as well as time, right? It is also correct because
No,
you
they choose the wave function depends on space, not time. There is a catch, sir.
why wave function your x y z
Yes,
t.
yes, yes. Whether you are taking this capital psi or small psi, it is not clear from this. Na?
Okay.
That is the problem. That's why I use these
Ah,
are the
ah,
options.
ah. Okay, then I would tell them to invoke the means revoke
If you are
the
going to
marks.
ask this small psi or capital psi, then
Hmm.
one can use the option.
Maybe they should have mentioned in bracket maybe that if the wave function bracket if they have mentioned psi, small
Yes,
psi or capital psi, they should have mentioned it.
yes.
Okay, I'll talk to the regular TAs who are involved in the question making and the answer. I will contact them. They are from my lab only, so no problem. I'll contact them. Then the integral is over space as well as time. That is not correct, but it should have been the wave functions. Okay, the wave function.
Can be
Okay,
anything. It can be capital psi or small psi. That's why.
it's a okay. It's
Yes,
a really confusing question.
yes,
Yeah,
yes.
okay.
That's why I choose only one
I
option. The
I think
integral is.
I think questions were set a long time back. I guess we need to change the questions also. Maybe okay, but you are going to get a new set of questions during the examination. Don't worry about that. In the examination, we will try to provide you the best possible questions or the best possible answers of that question, so that this kind of confusion is not there. Sorry for the problem. Okay, now question number 7. Periodicity of an electric field of the light is rewritten in the exponential rather than trigonometric form. Trigonometric form is the cosine form, right?
Yes, yes.
So you will remember the cosine form is uh,
Difficult to
was
handle.
yes, but you want to you also have a acha they I think missed.
They want to
No,
simplify
they
the
have not. They have. Did they miss? Yes, they have missed the. I think they have. Uh, no, no, they have not missed. This H, this perturbation term contains the your electric field, right? And that is a constant. So that constant is your Ex is going to be E0x multiplied 2 E0x sine or cosine 2 pi
new.
nu t, right? So this is actually now later on will be converted to the exponential term, so that from here you will going to get h nu 0 or
Mhm.
h nu naught, and from here you are going to get h nu, something like that. So that is actually to get rid of uh, no, not this, simplify the equation. The I part is still there,
Yes,
but to simplify the expression. Did you get this option correct or?
yes, yes.
Okay, good. Now question number 8. Phenomena that do not arise directly out of the time-dependent perturbation theoretical treatment of the problem of
Yes.
interaction of radiation with matter.
The
Which are the
spontaneous
two?
emission and non-radiative process.
Very good. These are the two questions. Out of these two, which one is mentioned in the Einstein treatment?
They didn't discuss the non-radiative process in Einstein
Okay.
treatment.
Okay, good. They before they used to say he, Einstein, right? Einstein treatment. So Anyway, so question number 9, induced emission is favored for. So if you remember, do you remember the relationship between A and B?
Yes.
I think I'm not sure. It is something like 8 pi. There a C cube was in the denominator. Nu was there in the, this nu was not the this nu, and I think cube was there, right? And maybe C, not C, but I think H. I'm not sure. Something was there, right? So, but if you remember up to this part, this might be enough. I guess so. Uh, Maybe, and obviously your B was there, right? This is your coefficient for absorption, and this is your coefficient for your uh, spontaneous emission. So now, if you see, the induced emission is favored.
That is for
Oh,
small energy gaps.
okay. So maybe if I turn this, induced emission is B, then it is going to be C cube A divided by 8 pi H mu Lm cube. So if the energy gap is less, then your new Lm is also going to be less,
Yes.
right?
Yes.
If this is less, if new Lm less, then the overall, then B
Molecule.
is going to
Yes,
increase,
higher.
right?
Yes.
Okay, so it should be small energy gaps, right?
Yes.
And what else? Molecule that absorb strongly. Obviously, a
Yes.
molecule have to absorb strongly, right? Then your absorption coefficient is almost is equals to your coefficient for the induced emission, right? So
Yes.
it would, so it has to be strongly absorbing. Okay. So if the question was something like, so this also comes from the background, right? That laser. So for laser, you need a the difference should be very less for lasing or the stimulated emission, right? So that's why it was said that the first laser that was invented was masers, microwave region. That is actually energy gap is small. Okay. Oh, then what I discussed earlier was actually, was it wrong? No, means obviously we are discussing energy. So during that neodymium laser, I told you no that the energy gap is less, but obviously the energy gap is more than the rotational states, but lesser the actually it is typically more than the what I'm saying. I think I'm saying a wrong thing. Your wavelength was more. Let me. That's why we should always look at the spectrum. That is the spectrum. The spectrum. So measure was microwave, right? Obviously.
Microwave.
So your rotational energies are less. So measures, and then your neodymium will come something like from here, close to the visible region. It is 800 nanometer, and this is 1064 nanometer, right? And then your visible region. Okay. Then actually I was confusing with the ultraviolet region. Anyway, so okay. With this, I guess we can discuss some of the numerical problems, and then uh, I will maybe we can solve these numerical problems tomorrow also. But let us actually have a look, and you can take a screenshot so that you can try to solve it yourself. Okay. So this question I given to you earlier also on the previous day. Okay. That day we could not solve, but we'll solve it maybe on the next day. Did you try to solve this question?
Yes, I tried this.
And are you successful?
Yes, that problem, I was able to solve that problem.
So
Yes.
can you tell me how what was your approach?
Is that new zero is new e into 1 minus 2 xc.
Your new, tell me
New
again.
e
Huh?
is this I have to first calculate the new e, then I have to divide it by the this is 4xc. You also need want to know this d, na?
Hmm.
This is
So
an
your
energy
new E by
divided
4xe, right?
4xc. Yes.
But how did you get new E? That's what I'm trying to.
Okay. That this you have already provided this that new
Zero.
how
New zero
yes
is provided,
yes
not new E is provided.
yes.
Then,
Then what I have done new zero is equal to new e into 1 minus 2 xc. Then new zero
right.
is 112 yeah, 1122.3.1123.4 is equal to new e bar minus 2 into 9. That new e xc also you have provided. Yes.
Uh, and why? And why did
New
you? Well,
this
why
new
not?
e
I should say. Huh? Tell me again.
this new zero bar is equal to new e bar. This one will be new e.
Okay. Wait. I will do it myself once. Huh?
Yes.
So for a simple, when we work for a simple harmonic oscillator, our energy E0 is, or maybe we start with EV is H plus, sorry, V plus half nu zero, right? Then for this it is your nu zero by 2, 1 is 3 by 2 nu zero. So the energy gap from 1 to 0 is nu zero bar. So when city is applied, I should say anomaly is invoked.
Yes.
Earlier, the assumption was that there is no anomaly, right? But when it is
Yes.
invoked, you are going to your energy expression changes. It
Yes.
changes to V plus half into nu E. This is at equilibrium, the
Mhm.
frequency, minus V plus half square E x. So your E0 is your half nu E minus 1 by 4 mu E xc,
Yes.
and energy of the first state, first excited state is 3 by 2 mu E minus 9 by
9 by 2.
4 mu E xc, and the energy gap is actually
This
uh,
new e into 1 minus 2
mu
xc.
E minus 2 mu
X.
E
E-
xc.
X. Yes.
Okay, now
Yes.
you will see that your when we work with SHO, so there we say the energy gaps are equispaced,
Yes.
right? So this is V equals to 0. So this is a potential energy surface, and it is a potential is half kx square, right? So it will follow a parabola. So your it is something like V equals to 1, V equals to 2, V equals to 3, something like that. But when anharmonicity is introduced, it actually changes
Most
to
potential. Most
Morse potential, right? So maybe I can use another color. So what we will see that V equals to 0 is remains almost the same. V equals to 1 is almost going to be the same. So actually the main, so at higher values of V, you are going to see that this value actually decreases.
yes.
but this gap is almost same.
Yes.
So for a lower value of these vibrational levels, huh?
Yes.
So there you can take this assumption and write that this energy gap obtained from the SHO, this is obtained from SHO, and this is after anharmonicity. So that is going to be equal, but that is still under the approximation. But the fact is, XC is very, 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 very small.
Yes.
That's why the change is not much here. But when your V value is going to be very, very high, that time the square term will increase, and that's when this term will the negative term will predominate, not predominate, but the negative term will show, and that's why the
Yes.
energy gap will decrease with time, with V increasing V. But the smaller vibrational level, you can write this. So you have been provided with nu zero, okay,
Yes.
and what else is provided? Your anharmonicity is being provided,
Yes.
okay.
Yes.
So you are able to get the new E. That is what you are saying also, right?
114 inverse.
Very good, very good.
Easily.
So that's how you have calculated new E. Now you got the new E, then obviously you got the
A value.
dissociation constant, a dissociation energy, right?
Yes. Yes.
But this dissociation energy is dE, not
Yes.
d0.
Yes.
But what is d0? So from, if I use this energy diagram only, so this is your dE, and this is your d0. So
Yes.
you know dE, and if you know the your 0 point energy,
That is
right?
already given. 1123.4 centimeter inverse.
Right. Then you can deduce that from dE, and you will
Yes.
get d0. So that how you can solve this kind of problem.
Yes.
I think this is a very good problem. You can practice. And obviously, another question is the rate constant, right? And rate constant is related to nu E is 1 by 2 pi k by
Yes.
m or mu.
Yes.
14 NF is given. So
Yes.
you calculate mu, reduce mass.
Yes.
You have nu E, you know 2 pi. So you will be able to calculate the force constant also. So you calculate 0 point energy and obviously the bond dissociation energies. So using this only, I have provided some more questions that determine nu E, force constant, and harmonicity, 0 point energy from here. Okay.
Yes.
So here what you need to do, let's see, 0 to nu. That means here see, this is your fundamental. This is related to your fundamental. This is related to your first overtone. This is related to your second overtone. You don't have to bother about this. If you write down the equation for this, again you are going to get the anharmonicity, right?
Yes.
You are going to
From
have three
from
three
first
equa-
equation I can get this.
yes,
From first two equation I can get the two unknowns like
yes.
GE and this
For
basic.
two unknowns, you need actually two equations, so that you can do it even from the first two, right?
Yes.
Yes. I and the similar question is there on the next problem also. Here, I think this problem we have already discussed, or this is we have not discussed that. I think this we have discussed in the previous day. If we have not, the method is the same. The fundamental and the first two overtones are given, and then determine nu E, force constant, anharmonicity constant, 0 point energy, and bond dissociation energies. So actually, see, similar kind of numericals, I thought that I will solve one and I will keep one for you. Better if you try it yourself, then the concepts are clear. you remember the formulas and which are important, going to be important for the exam, right? I
Yes.
think this question is also we have discussed in the previous day, I guess. Similar kind of questions. So then again, this question I think we have discussed that first five vibrational not required. Only two will be suffice, right?
Interesting. Yeah.
Yes. So then actually we again come to the assignment problem, but okay. So maybe we'll solve one on the next day, but obviously as I told you, I'm actually going home. Today is my flight, so I will be returning on 5th March.
Okay.
So 5th March, then 4th March, I'll actually will not be available. Maybe after reaching here, maybe on 6th, I will take a extra class. Maybe on not on 6th, maybe on Saturday or Friday. Um,
Yeah.
which day you are available?
I am available after office. I am available.
After office, you are available. So maybe Saturday, is it a holiday for you?
Yeah, Saturday, Sunday is holiday for us.
But you want to chill or you want to join the class?
No, no, not at all. I am available.
Okay, so
Yes.
maybe we will take it on 8th.
Yeah,
So
yeah.
I will talk to the concerned person. So I will mail it to them that I will change the schedule once for that week. Okay. So then I will try to solve. I will take. I will try maybe on Saturday if I get time after coming back from home. I will try to gather some more numerical questions from Banwell. Uh, you can get the manual from online also. Actually,
Yeah.
I could not share that thing with you because then some copyright issue will be there. But you can find it in the Google. You know better than me how to get it.
Yes, yes.
So try to look at the questions. We'll discuss some more numerical questions. Okay, with that,
Happy,
I
happy
thank.
journey.
Oh,
Yes,
thank you very
happy
much.
journey.
Thank you very much. My flight is at 1 a.m. So
Okay, okay, okay.
it will be a red eye flight.
Yes,
So
yes, yes.
um, okay. So
Okay.
thank you for
You are
joining.
proper. You belong to which place, sir?
I belong to West Bengal, Bakuda.
Babughat. Okay.
No, Bakuda,
I'm
Bakuda
also
district.
I'm also from West Bengal.
That I know. That I know. But from where?
This Kathi, this near
Kathi.
to Digha. Yes.
Okay, I know, I know. Actually, I am from Bakuda, not Babugat.
Okay.
Bakuda district.
Okay. Okay. Okay.
Uh, so
Have a happy and safe journey.
thank you very much. Thank you very much. You too have a good weekend, good week, and maybe a good weekend also.
Yeah. Yeah.
Okay,
Thank you.
with
Thank
that, let us stop today. And
you.
thank
Yes.
you for joining again. As I hope you will join on the next day, on the 8th,
Yes. 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 Yes.
8th
Good
March.
night.
Okay, good night. Thank you.
Bye.